Session 2002-1, exercise number 1. So it's the conservation and non-conservation of the mechanical energy. We'll start with the given. So consider a material system S formed of an extensible and massive string of length. So we have the length, having one of its ends at the point O, and the other is carrying a particle P here of mass m equals 0.1 kilogram. So S is shifted from its equilibrium position by theta maximum equal to 90 degrees. This means it's here at this point. While the string is under tension and then released without initial velocity. So without initial velocity, this means V at the point D here is equals to 0. Take the horizontal plane passing FA as a gravitational potential energy reference. So here we have the reference. And we neglect friction on the axis through O and air resistance. So when we say there's no friction, this means I must know that I must use the law of conservation of ME, mechanical energy. Now we'll start with the first question. Calculate the initial mechanical energy of the system when P was at D. So in order to find the energy, we say system is S and Earth, and we must find ME at the point D, which is equals to KE at the point D plus PEG at the point D. Now KE, it's half mvd square. We already said that it will be released without speed, so this will be equals to 0, plus mgzd. Now since it's above the reference, this is the reference here, d is above the reference, then it's positive, so it will be mg plus hd. And here the height here, if you notice, so this is the height d, which is the same as this part, and this is the length of the string. So which is equal to 0.45 meter. So it will be equal mg times L, and we have all the numbers, so it will be equals to 0.45 joules. This is for the first question. Now, second question, part B, determine the expression of the mechanical energy in terms of L, m, g, v, and theta, where v is the speed of the particle when it's at the position making an angle theta with the vertical. So I want now to find the mechanical energy, but the expression at this point. So the same system, we are studying the same system. The mechanical energy at the point P is equal to KE at the point P plus PEG at the point P. Now KE, it's half mv square, and it's term of mmv, so it's done, plus mgz at the point P. Now we still have to find z of the at the point P. It's above the reference, so this is the reference here. This is the height here, h of the point P. It's above, then it will be equal half mv square plus mg height of the point P. We still have to find this height. Now in order to find this height, this is HP, so I can do a parallel here, and then I will put here a point I. This means the height here is equals to IF. So height of the point P is equal to IF, which is equals to OF minus OI. So it's OF, and we continue. Now OF is the length of the string, but OI, how do we find it? We notice that this part OI here is adjacent to the angle theta. And since it's adjacent, then we use cosine theta. So cosine theta equal, the adjacent is OI, over the hypotenuse is OP. But OP itself is the length of the string also. وزيته طول الشريط. Then this is also L. So we notice that OI equals to OP cosine theta. This means L cosine theta. So it will be minus L cosine theta. And here I can substitute, so it's equal half mv square plus mg bracket L minus L cosine theta. And this will be in terms of the unknown given. Part C, determine the value of the angle theta for which the kinetic energy is equals to the gravitational potential energy. So what do we have here? Condition, we have KE equal PEG. But we know that the mechanical energy is equals to constant, since there's no friction. And which is equal, we already found it, which is equal to 0.45 joules. But we also know that the mechanical energy is equal to the kinetic energy plus PEG. And this is our condition here. So here 0.45 is equals to. This means instead of KE, I can substitute فيه يحط محلها PEG. So it will be PEG plus PEG. So equals to 2 PEG. And then I can continue the substitution. So 0.45 equals 2 times. Now PEG, we already find it, which is equals to mgz. Now this z is at any instant. So if it's at any instant, as if for example is the point P, then it will be equal 0.45 equal to mg, and z, yeah, that's it, here. So it will be L bracket 1 minus cosine theta. خدنا L common factor. And now the question is to find who? The question is to find the angle theta. So now we'll continue the calculation. Then we'll have here as هذه كلها is equal to 0.45. So the angle here implies we have the mass is equal to 0.1 and we have G is 10. So بيطلع لنا here it's 1 and we still have here 2. Now the length is equal to 0.45. So we'll have here 0.45 equal 2 times 0.45. So it's equal to 0.9. 1 minus cosine theta. This means we'll have 1 over 2. So here the answer is 0.45 over 0.9. So here we'll have equals to 0.5 equal 1 minus cosine theta, which means that cosine theta is equal to 1 minus 0.5, that is equal to 0.5. And here I can do it on the calculator and then find that theta is equal to 60 degrees. Now, we continue the next question. Calculate the magnitude V0 of the velocity V0 as it passes through its equilibrium position. So now this pendulum reaches the equilibrium position here. Okay, so it passes from D to P until reaching this point. The question is to find the speed here at this point. So in order to find the speed, we still have a conservation of mechanical energy. So the system is the same. The system is S, or the pendulum P, and the Earth. The mechanical energy, we have conservation of ME. So the mechanical energy at the point F is equal to 0.45 since it's conserved. And at the point F, I have KE at the point F plus PEG at the point F. But we know that at the point F, the height is 0 since it's on the reference. Here is the reference. Then here we'll have half, so this is 0. So it's half mv0 square. They're said it's 0.45. This means, and we have the mass. So here we'll obtain that V0 is equals to 3 meters per second. Part 2. Upon passing through the position of equilibrium, the string is cut. So now this string is cut and P enters in head-on collision with the stationary particle P1 of mass M1 equals 0.2 kilogram. So this means I have here another particle which is P1, and this particle P here enters with a head-on collision. So here we have a collision now. So before the collision, let's write the condition. So before the collision, P had a speed V0 equal 3 meters per second, while P1 had a speed V equal to 0 since they said its what is stationary particle. Okay, so this is for the first particle, but this is after. Now after collision, we'll continue the given. P1 is projected with the velocity V1 of magnitude V1 equal 2 meters per second. So after the collision, I have P1 V1 equal to meter per second. Determine the magnitude V of the velocity V of P right after the impact. So now here P after the collision has a velocity V which is unknown. The question is to find it. Determine the magnitude v of the velocity just after impact, knowing that they are collinear. So here, since we have collision, this means I have conservation of linear momentum, which means that P before the collision is equal to P after. And here this means P for the first particle, so it's P plus P1 is equals to P prime plus P prime 1. And then I will substitute. Before the collision I have here the mass, it's M and V0. For the second one it's 0 since it's stationary. And here it's equals to mv is to find, plus for the second particle it's m1 v1 vector. But since the velocities are collinear, so I can remove the vector and then I can write it like this. So it's mv0 equal mv plus m1 v1. And the question is to find this unknown here. So I can continue here, implies the calculation. So v will be equal to mv0 minus, I take this one here, and over small m, which will be equals here to minus 1 meter per second. Now we continue, and the question is the collision elastic? Justify your answer. So in order to know if the collision is elastic or no, what should we do? We should find KE before and KE after the collision. So KE before the collision is equals to KE for the particle P plus KE for the particle P1, which is equals here to half. We have equals to mv0 square, but this is 0 since it's stationary, so we'll obtain 0.45 joules. For the second one, KE after the collision, also is KE for the particle P plus KE for the particle P1, but this is for what? For after the collision, which is equal to half mv square, we already find it now, plus half m1 v1 square, it's given. Then we'll obtain as answer 0.45 joules also. And since we have KE before is equals to KE after, this means that the collision is elastic. And now P1 being projected with the speed v1 equal 2 meters per second, it moves on the frictionless track FA and then rises at point A with the speed v1 along the greatest, so with this speed v1, and then reach the inclined plane making an angle alpha 30 degree. So since we have, suppose that there's no friction, so if there's no friction, then this means ME is conserved. So determine the position of the point M, for which P1 turns back. So the system is P and the Earth, and we know that it's P1, sorry, and the Earth, and we know that there's no friction. This means ME is conserved. So ME at the point A is equal to ME at the point where it will turn back. So turn back, I write it here, turn back. When a particle turns back, this means it reached the highest point. So this means at this point, the speed is equal to 0. So what do I have here at the point A? KEA plus PEGA equals to KE at the highest point. Let's suppose, for example, this is the highest point, which I'll name, for example, I will name it M. So it will be KE at point M plus PEG at the point M. And since it turns back, then this is equals to 0, speed equals to 0. And then here I can substitute, so it's half mv1 square, but at the point A there is no height. Height is equals to 0. So equals, we still have M, this is M1, G, and Z of the point M. Now at this point, the height, it's above the reference, and then it's plus. So Zm is equal to plus Hm, which is equals to, if we notice here, so it's opposite to the angle alpha. So this height, then we'll use sine alpha. So it will be Am hypotenuse sine alpha. And then here we'll have m1 and m1 are simplified, so it's half v1 squared is equal to g times z, which is am sine alpha. And the question is to find the position of the point m at which it turns back. So this means I must find am. I have g, I have v1 is equals to 2 sine 30. Then here I can find am, and we'll obtain then am is equals to 0.4 meter. Now part B, in fact AB is not frictionless, so P1 reaches a point N and turns back, where AN is equal to 20 centimeter. Here if you notice it's 0.4 meters, so it's 40 centimeter. When we have friction, the value is now less, so it's 20 centimeter. Calculate the variation in the mechanical energy of the system P1 Earth between A and N. So delta ME between A and N is equal to ME at the point N minus ME at the point A. And I continue the substitution, so which is equals to ME at the point A. We already we can find it, so we'll have here as answer it's equal mg z, since at the point A N there's no kinetic energy, so here ME at the point N is KE at the point N plus PEG. But since it's the maximum point it turns back, then this is 0, so we still have PEG. And ME at the point A is also KEA plus PEGA, but also there's no height here, so since there's no height, then this is equals to 0. We still have this one, so it will be here mgz at the point N minus KE at the point A. So we only substitute, then it will be here mg an sine alpha. So instead of reaching m, it reached the point N, but the same way to find the height, minus half m1 and v a square, which is v1, which is equal to 2 meters per second. Then now I can substitute all the numbers, and I will have as answer minus 0.2 joules. The question is then to calculate the force of friction. We know since if we have friction, then we'll use the law of variation of mechanical energy, which give us that delta ME is equal to the work of the friction, which means that minus 0.2 equal, now what's the work of the friction? Minus F times displacement. And on the inclined, this displacement is who? It's from A to N, so it's AN. This means that minus 0.2 equals to minus F times AN. I have the value AN is 0.2 meter, so this is 0.2 meter. And then I can find F, so we'll obtain F is equals to 1 Newton. This is the value of the friction.